This is going to be the state of GPU rendering in 2019. My name is William George. I'm one of the folks here in our labs department at Puget Systems. What do we want to accomplish in this webinar? We're going to try and cover several topics related to GPU rendering. We're going to give an overview of what GPU-based rendering is, just in case there's anybody with us that isn't as familiar with the technology or what it is, just to make sure we're not leaving anybody behind, and then why it's gaining in popularity. We're also going to go over the advantages and limitations of GPU rendering, some recent advancements in GPU technology that are going to be impacting GPU rendering performance in the future, particularly NVIDIA's RTX and NVLink technologies, but there's some other stuff too. And then where to spend your budget if you're getting a new system to make sure that you get the best performance, whether it's a workstation or a remote server you're going to be using in a render farm, those sorts of things. And most of this is going to be fairly general information about GPU-based rendering. If you're actually in the market for a system right now or going to be in the near future, we highly recommend speaking with one of our technology consultants. They're going to be able to give you much more personalized recommendations and look at your exact situation and budget and needs and what software you use as a whole instead of just GPU rendering, kind of give you a more holistic picture and recommendations tailored to your situation. And of course, please ask questions. If anything comes up during the discussion here, you don't want to forget about it. There's actually a way at the bottom black bar on the webinar. You go to the Q&A button that you'll see there, click on that, and it will bring up the question and answer section where you can type stuff in even ahead of time, and it'll keep track of it so that we can spend some time at the end answering any of those questions that you may have. And that'll be available during the whole webinar and at the end, so you can ask those questions at any point. And just for a little bit of background about us here at Puget Systems, we are a workstation manufacturer, but we specialize in custom high-performance workstations, and we put an emphasis on the personal consulting and support. We want to make sure you're not just getting a computer from us, but you're actually partnering with us with a team of real people, and we're dedicated to freeing your workflow, removing obstacles, making it so you can focus on being creative and getting your work done, rather than on what sort of hardware to buy or the nuances of keeping it working well. And if you're not looking for a system, or if you want to build yourself or just want some more background information, we also put out a ton of content on our website. There's two main sections I'd recommend you look at if you're interested in that sort of information. One is our solutions, which are actually sort of the hardware recommendations we have for different applications. And you can go to PugetSystems.com, that's our website, and then along the top navigation bar, there's a big section called Solutions, and then it's broken down by category. There's rendering, photography, post-production, photogrammetry, all sorts of different professional applications that we focus on, and you can find tons of information there. Or if you're more interested just in the technical details, the performance side of things, not so much hardware recommendations, you can also go to Publications, and then we've got articles, blogs, case studies. The meat and potatoes, really the sort of stuff we're going to be talking about today, is mostly in the articles section. And you can even filter there, as you can see on the screen at the moment, by different types of applications and things like that, if you want to narrow down to just the sort of content you're interested in. So to get into the main topic here, why GPU-based rendering is gaining in popularity. And to explain that, we kind of have to give a little bit of background on what rendering is. And again, just to make sure that we're not leaving anybody out here. If this is stuff that's all familiar to you already, I do apologize. Please hang with me for a couple minutes. So rendering is the process of making a photorealistic image or a set of images, if you're doing a video, normally via ray tracing or path tracing, which is a subset of ray tracing. I'm just going to use the generic term ray tracing now, even though technically some of this stuff is actually path tracing instead, but it's a little bit easier just to keep one term in there. This sort of work, rendering and ray tracing, takes a lot longer to calculate than what's called rasterization, which is kind of the normal thing used in a lot of real-time graphics in video games and virtual reality and augmented reality. But proper rendering results in much more realistic images. It also handles things like lighting, reflections, transparency, and shadows much more accurately than a lot of the other methods used. So you end up with a picture that looks really realistic, rather than one that you can tell is from a video game or something like that. Rendering is used across a wide range of disciplines and businesses. Film and animation, there's whole films at Pixar and DreamWorks, those are completely rendered. And even in a lot of other movies, special effects and things are done this way nowadays instead of physical, practical effects, because it's a lot cheaper and less destructive in a lot of cases to do it this way. And it's also used in architecture to provide photorealistic images of what a building might look like, or interiors, things like that. And then in product design and engineering. And in fact, it's kind of funny, a lot of product photos you'll see on Amazon and other places can actually be 3D renders rather than real products that they photographed. You can kind of tell sometimes, but sometimes they're so realistic it's hard to tell them apart. So why the shift to GPUs? Because rendering's been around for a long time. Ray tracing started out on CPUs decades ago, and way before the idea of even a dedicated graphics processor, which is what a GPU is. CPUs, by their very nature, are very flexible. They can run any kind of code, and they're usually fast at doing one or two things at a time. Modern multi-core processors can handle a few, but ray tracing, because of what it's doing, requires millions of separate calculations. If you're ray tracing an image for a computer screen, you're going to need multiple rays traced for each pixel on the screen to get a good, proper color and image. And if you're doing something for print or for video with high resolution, it can be far more calculations than that. Every frame, especially in a movie or something, you're going to have tons of time taken up by these. It could take months just to render videos out for movies. So GPUs, when they came on the scene, they were built to handle a lot of small calculations at the same time, instead of a few more complex calculations. And for years, that was limited to really only handling rasterization for games and things like that that needed real-time graphics. That was what GPUs were for, after all. But in 2007, NVIDIA released video cards with a new GPU design, a new architecture, which they called Compute Unified Device Architecture, or CUDA for short. And that allows all sorts of non-graphics code to be run on video cards. You can run physics and all sorts of other things. Anything that needs a lot of little calculations that don't depend on each other. And within a few years after that, GPU-based rendering engines started to show up on the market. By using GPUs instead of CPUs, a lot more rays could be traced at the same time. And especially early on, each individual calculation wouldn't go as quickly on a video card, but you could be doing hundreds or thousands of them instead of a few at a time, which in the long run saves a whole lot of time. CUDA also, just by its very nature, supported spreading calculations across multiple video cards, allowing for higher performance scaling within a single system. On a CPU-based rendering engine, you might be able to get 1 or 2 physical CPUs, maybe 4 or 8 in a really large rack mount. With video cards, you can easily put 2 to 4 in a single workstation, 8 or more in a rack mount, and each one, again, is far faster than a CPU when it comes to these sorts of calculations. GPU performance has also been increasing at a much greater rate than CPUs. There's some really good graphs for this out there. I wasn't able to find any that weren't copyrighted, but it's probably in the ballpark of about an order of magnitude more increase in performance that GPUs have seen over the last decade compared to CPUs. And we've only gone from having maybe 2 to 4 cores in a CPU up to, on the high end nowadays, 18 to 32. So it's a substantial increase on the CPU side, but GPUs have easily increased by about a factor of 10 over the course of the same time period in terms of performance. So a much bigger increase per GPU. And again, being able to combine that with stacking lots of them in a single system is pretty tremendous. But it's not all perfect. There are also some limitations to GPU-based rendering, so we're going to talk about some of those. And we've already gone over some of the advantages: better performance than CPUs, built to handle parallel calculations, things like that. Another advantage that GPUs have is they're also easier to upgrade. With a CPU, if you, a couple of years down the road, want to go to a newer CPU with more cores or something, odds are you're going to have to replace the whole motherboard, cooler, possibly RAM. It has a lot of knock-on effects. Might even basically be a whole new system at that point. Video cards, you can actually go in and swap out all the video cards in a system without really affecting much of the rest of it. They've used the same standard for connecting into a system for years. That's not likely to change anywhere in the near future. So that gives you sort of a better option for upgrading mid-cycle before you're ready to purchase a whole new set of systems if you want. But on the limitation side, you do have the limitation of the video memory, VRAM, on each video card. That's going to limit scene size and complexity. In general, with some exceptions, video cards are usually going to have less memory than a whole computer system will. And each GPU, each video card, needs to have all the scene data so that it can do the ray tracing, so you don't have a situation where the video card memories are added together. Um, and some rendering engines can store certain types of data outside of the video card, but even if they're able to do that, which is called out of core memory, there's going to be some performance impact, whether it's a little or a lot, depends on the engine and what sort of data and how much data you're storing out of the video card. But it's something to keep in mind. And you can combat this somewhat by just going higher end on the video card selection. Top end video cards do come equipped with more RAM, but they also get more expensive. Another limitation, not so much of the video cards, but of the GPU engines as they stand now, is that not all the materials and lighting and effects that 3D design applications use are necessarily supported on all GPU rendering engines. If you're moving from a CPU rendering engine to a GPU one, you're probably going to have to make some changes to your scenes, adjust the lighting and the material libraries you're using and things like that. But that's something that's getting better. As more engines are adding GPU support, and as the GPU-based engines have just been in development for longer, that stuff's going to get better and better over time. So, moving on from sort of just an overview of GPU rendering to advances that are going to be affecting it, there's some pretty big ones. In particular, the biggest is NVIDIA's new RTX technology. That's been featured on the latest generation of their video cards. You'll even see RTX in the model name of the video card, is how you can tell if it's one that has this technology or not. But it's actual ray tracing hardware on the card now, instead of depending on those general purpose CUDA cores, which were what enabled ray tracing to be done on video cards to begin with. They've seen how important doing that is on cards, and they've actually dedicated a section of hardware on video cards now specifically to ray tracing. And you see that a lot in pop media and stuff talked about for video games, being able to add shadows and lighting and stuff to those that are more realistic. But it's going to have a big impact in proper ray tracing as well, because it can go even faster. But the downside is rendering engines need to be rewritten to use it. They've been written in CUDA for years now. They have to be adjusted to utilize this new RTX hardware. So that's a process that's ongoing, and we'll talk about that a little bit more when we cover some of the different rendering engines that are out there. Another hardware feature in recent NVIDIA cards in this same RTX series is called tensor cores. And they're not specifically related to ray tracing. What they're actually for is speeding up machine learning algorithms. But a lot of the folks who are developing RTX technology for ray tracing applications are looking at using machine learning to do things like noise reduction and other post-processing after the main ray tracing is done to make the images look even better. So that's just something to be worth knowing about. Another technology NVIDIA has debuted, actually came out just before the RTX technology in the earlier generation of cards, is called NVLink. And it's an optional high-speed connection between a pair of video cards. There's a picture there of the physical NVLink bridge that connects the two cards. It requires the cards support that. It also needs support at the operating system and application level. But when all that is there, it dramatically increases the speed at which cards can communicate between each other. Instead of having to go through the motherboard and PCI Express connection, they can talk directly, which results in about a 5 to 10 time increase in their communication bandwidth. Now, that doesn't do anything on its own. Just having that faster connection there isn't going to be helpful. What actually has to happen is that rendering engines and other applications have to be written to take advantage of that. But it enables things like potentially memory sharing, or maybe both cards don't have to keep everything in memory. They can share some of the data and send it back and forth quickly enough that it would increase performance compared to having it out in the system memory or something like that. It is also worth noting, though, that NVLink only connects 2 cards at a time. So you can't have like 4 cards all connected together on NVLink. It would be 2 NVLink pairs, but that is still an improvement over just having individual cards. And then a third advancement that's going on isn't so much hardware related as it is software. NVIDIA's CUDA has sort of been the bones holding all of this together in terms of rendering for a long time. So almost all current generation GPU rendering engines use CUDA. And because of that, they can only use NVIDIA graphics cards. Khronos Group with Vulkan is aiming to change that a little bit. Vulkan's a cross-platform graphics and computing API. So it'll work on NVIDIA and AMD cards and even other hardware. And some rendering engines are looking at moving toward that in order to support a wider range of GPUs, allow for more options, that sort of thing. But at the moment, AMD cards lack any hardware ray tracing. It's something they've talked about, but none of their current generation of cards have it. So for the moment, at least, even with Vulkan out there, when that starts to hit the market in some rendering engines, NVIDIA RTX cards are still probably going to be the fastest option for the near future. Moving on a little bit to an overview of GPU rendering engines, we're going to hit three of the big ones that are out and that we've done a lot of testing on here at Puget Systems. There are others, but these are kind of some of the big names. The first one is OTOY. They make OctaneRender. It was one of the first GPU rendering engines released back in 2012, so it's been around for a while, and it has great performance and flexibility. It's got near perfect scaling across multiple video cards. In other words, each video card you add basically gives a full 100% increase in performance compared to the one before it. It can also scale even further across a network of machines if you have the right licensing. Their licensing is a little more complicated. And it's available in both standalone editions as well as plugins for many of the popular 3D applications. And that's actually something that's going to be true of all three of these rendering engines we're going to talk about. And there at the bottom, we've got some graphs just kind of previewing performance a little bit across some of the current generation of NVIDIA GeForce and Titan cards. And this is actually one of the ones where they've got RTX in their beta version, basically the demo version that they're kind of working on. And you can see at the bottom there is the normal version now, Octane Bench 4 versus Octane Bench 2019 with RTX enabled. And it's almost a 3 times increase in performance. And that's sort of a best case scenario, but it's pretty substantial. It's going to be a big deal moving to this RTX stuff. I'd say for most folks anywhere from a 50% to a 300% increase in performance, depending on your scenes and things like that. One thing with OctaneRender that I have noticed is that they tend to lag a little bit in support for new hardware. For example, our RTX stuff that's been around for nearly a year still is coming in the next generation of their software. They're also still working on NVLink, but that's kind of the case with any of these rendering engines. It's going to take them a little while to adapt to new technology as it comes out, but they've done a good job of working on keeping pace with that. The next engine we're going to talk about is Redshift, which has been around for a while. It used to be its own standalone application, its own company, but they were recently acquired by Maxon. They're the folks that make Cinema 4D. And it's also got good multi-GPU support. The scaling's not quite as good as Octane. We see about a 95% gain from each additional card rather than a full 100%, but it's still very good. It's also more heavily impacted by PCI Express lanes, which we'll talk about a little bit later in the hardware section. And they've got a limit of 8 GPUs per session in Redshift. But practically speaking, unless you're doing something crazy, that's the most you're going to have in a single system anyway. If you did somehow have a single system with more than 8 GPUs, or if you were using stuff across a network, you can actually split it up into multiple sessions and have 2 or 3 different renders going with smaller numbers of video cards if you'd like. And again, there we've got a graph performance. In this one's time in seconds rather than some sort of score, but you can still see that there's a nice progression from the mid-range cards up through the high end in terms of the performance gain. Redshift is also notable. It was one of the first that had really good out-of-core memory support, especially for textures that were too large to fit in the VRAM. So that's something to be aware of. And again, like Octane, they've got RTX support coming in the next generation of their software. In terms of the third software package we're going to talk about is V-Ray Next. That's from Chaos Group, and V-Ray's actually been around for a long time. It started out as a CPU-based engine back, I think, in the 1990s, maybe somewhere back there, but they added GPU support in 2009, so not long after CUDA came out. The current GPU version of their engine actually can also emulate CUDA on the CPU for additional performance boost, but it's kind of small compared to adding another GPU. I included graphs here showing on the right-hand side that you don't gain a whole lot. Even a high-end CPU like Threadripper or a Core i9 isn't as fast as a moderately high-end video card like the RTX 2070 Super, but getting a decent performance boost like that, that's half the speed of another video card for free, no additional cost to you or anything if you've already got the CPU in your system, isn't a bad way to go. It's also very good at multi-GPU scaling, again, more on par with Octane in terms of just about perfect scaling. And again, like all the others, RTX support is coming in the next major version. V-Ray Next is also one of the ones where it's actually two engines. They have a CPU engine still and a GPU engine, and they are somewhat separated. There isn't complete cross-engine feature support. So if you're moving from V-Ray CPU to GPU, you will need to make some adjustments, but that's something they're working on, closing that gap and making it more of an exact transfer. And there are other engines. Like I said, those are kind of the three that we've done a lot of testing on here. But just in the last year or so, a lot of other engines have announced that they're adding GPU support, even ones that for years were staunchly CPU only. Autodesk Arnold is getting GPU support. It's actually in their current beta version. Pixar with their Renderman XPU is what they're calling the version that works on CPUs and GPUs. And then Keyshot has announced that version 9 that's coming out very soon is going to have GPU support as well. And it's really just gotten to the point where the performance increase available from GPUs, especially with RTX coming, is just too good to pass up. I think any of the engines that stay purely CPU only are going to eventually find themselves in the dust in terms of performance. So moving on to recommended hardware. This will apply to both workstations and servers, and buying your own, or if you're looking for advice on what to buy from a manufacturer like us, we're going to kind of try and cover all that. First of all, starting with sort of the platform that you're going to build this on. In terms of the CPU, performance of the CPU itself isn't a huge factor. You don't need a high core count CPU or anything like that, nothing big and expensive. But what we do strongly recommend is at least one core per video card, and ideally a couple extras. That way, anytime that something is going on that a video card needs a little bit of CPU time, there's a CPU core there available for it. Also, keeping the clock speed as high as possible is ideal, because when you do hit a step of some sort of processing that's CPU related, you want it to get done as quickly as possible so you can move back over to the GPU-based calculations. So keeping the clock speed on the CPU high, not a ton of cores, but at least one per video card you're going to have in the system, maybe a couple extra. RAM is also not a huge factor. You don't need hundreds of gigabytes unless you're going to be doing something weird or very complex where your scenes far exceed VRAM. What we recommend, though, at minimum is aiming for twice the amount of VRAM you have per card. That usually ends up meaning somewhere in 32 to 64 gig range is going to be plenty for most folks. If you think you are going to be using out-of-core memory, you can go even higher, or get a platform that has extra RAM slots available so that you can add that later on if you need. On the drive side of things, this isn't going to have a huge impact on the actual performance when ray tracing is being calculated, but uploading all of the data from your scene into the video cards for calculations and then saving the files and stuff after they're done rendering, there's little things that are impacted. So a fast solid state drive is ideal. It'll also impact things like how smooth windows and applications feel when you're interacting with them. So we strongly recommend that these days. SSDs are also more reliable than traditional hard drives. There's no moving parts to worry about, things like that. Hard drives can still be okay if you need extra long-term storage or backup, but definitely, if at all possible, SSDs and faster ones when possible for your OS applications and working files. And then sort of more the less flashy hardware, the motherboard, even though it's not something a lot of people think about a ton, it's what everything plugs into. So you don't want to skimp out there. You're going to need one PCI Express X16 length card slot for each video card in the system. And there's a little chart there kind of showing the different sizes visually so you can see what they're like, but almost every video card uses an X16 connection. Now, a lot of motherboards, when you have multiple cards, we'll start to lower the speed of the connection to X8 or X4, which can have a small impact on rendering performance. Most notably, as I mentioned earlier, Redshift actually suffers more, especially when you hit X4 speed. X8's usually not a big deal on any of them, but that's the electrical connection, the signal that's being sent. The physical length of the slot still needs to be an X16 for the card to physically fit in. If you just have an X4 or 8, usually the cards are just not going to be able to fit into that. So that's something to watch out for when you're picking motherboards. And the motherboard selection is also going to affect the CPU you can have, the RAM, the number of drives, the I/O panel connectivity on the back. So definitely keep that in mind. And also the power supply, again, another one of the components that's not really thought about a lot, but it's what keeps everything powered and running. So you don't want to skimp there either, because video cards draw a lot of power. Up to 300 watts, that's the maximum PCI Express spec. There have been a couple cards that exceeded that in the past, but generally speaking, 300 watts is a safe estimate on the high end. Mid-range cards don't even use that much, but that kind of gives you an easy way to just calculate a safe number for power supplies. If you take about 300 watts for the base system for most, again, unless you're doing something crazy, and then 300 watts per card, you can really easily get a ballpark estimate for how much power you need for the whole system. And we've got kind of a chart there showing that. And then on to GPU selection. So this is the meat and potatoes here. Within a given video card line, the higher end cards generally are faster at rendering, but the performance increase rarely matches the increase in price. In other words, a $1,000 video card usually won't render twice as fast as a $500 video card. But there are some trade-offs. Those higher end cards tend to come with more onboard VRAM. And you can even kind of see, we could put together a little performance chart, and this is rough, this is not exact, but ballpark speaking, the Titan RTX, which is 24 gigs, is roughly on par with the Quadro RTX 6000 and 8000. And as you can see there, the 8000 has 48 gigs of RAM, so you have an option with double the video RAM. Likewise, the RTX 2070 Super 8 gig is roughly on par with the Quadro RTX 5000, but the 5000 has double the memory. And in fact, well, we'll talk about the memory here a little bit more in a minute, but one of the things that you kind of end up seeing, I didn't include pricing there because that fluctuates, but if you look at prices of video cards, what you'll find is actually the sweet spot tends to be multiple video cards rather than a single high-end card. So again, for example, the Titan RTX is a nice fast card. The 2080 Ti is not quite as fast, but you can get two 2080 Ti's for about the same price as a single Titan, and they will far outperform it. But the downside is they have 11 gigs of VRAM each instead of 24. So that's the trade-off usually. Fewer cards will render faster as long as that's not causing you to hit a cap on your scene size and complexity with the amount of VRAM that's there. So talking a little bit more about that VRAM, if your scene data is too large to fit in the memory, depending on the rendering engine, it might just slow things down if it has to use out-of-core memory for some of that. Or in some cases, it might fail to render entirely. So you do want to make sure you get enough VRAM for what you plan on doing. And again, as we kind of saw in that chart before, Quadro cards have more VRAM than GeForce. Usually there's some comparisons where it's not the case, but for the most part, but they do cost a lot more money. Prices tend to be about 2 to 3 times higher for a Quadro with the same performance as a GeForce card, but you usually get about 2 times the memory as well. One thing to keep in mind with that price increase, it can sound crazy at first that it's 2 to 3 times more expensive and the only thing you're gaining is VRAM. But that's if you're just looking at the cards individually. What you should be doing when you're kind of trying to spec out at least a whole system, if that's what you're pricing out, is look at the price increase from one card to another in the context of the whole system. So let's say instead of talking about a $1,000 versus a $2,000 video card, maybe if we're talking about a system that's $2,000 at the base plus the video cards, now we're talking about a $3,000 to $4,000 price difference, $1,000 there, what, a 33% increase in price. But if you're gaining double the video memory for that and it enables you to do larger, more complex rendering, that might well be worth it. So just keep in mind that looking at price comparisons just on the video cards by themselves doesn't really give you the whole picture. You want to look at the price differences between different video card options, whether it's models or quantities of video cards in the grand scheme of the whole system. And that really applies to everything. That applies to CPUs and other things as well. It's better to look at it as the whole price rather than just the components. It's also worth keeping in mind, and again, this is something that none of the current rendering engines do right now, as far as I know, but I believe they're all working on developing it, is NVLink. When that becomes something that those engines use, if they're able to utilize it to share memory, which is kind of what everybody seems to be expecting and aiming for, that will help alleviate some of the memory limitations as well. But again, you got to keep in mind that does require the application to support it, as well as the operating system, and you have to physically have the NVLink bridge between the cards. So if you're getting a system now, even if the rendering engine you're going to use doesn't immediately support NVLink, it's not a bad idea to go ahead and get a system with the bridge so that you're all ready to support that when it's added. And then final thing here on the GPU selection, and this is actually really important, even though, again, it's not something a lot of people consider, is cooling. A lot of the consumer-oriented video cards, the GeForce and unfortunately even the Titan, have multiple fans for cooling. And that's fine for a single video card, in a gamer system or something like that. That's kind of what those are intended for. But the problem is those multi-fan designs just blow heat back into the system. And again, with one video card, not a huge deal. But what you really want is a single fan video card that exhausts the heat out of the system. Because if you're talking about having 2 or 3 or 4 video cards, that's hundreds of watts of heat you're needing to dissipate, and pumping that back into the computer means everything else in the system is going to heat up too much, including the other video cards. And that'll lead to slowdowns and performance degradation. You want to get that heat out of the system as fast as possible. So you want single fan cards that exhaust heat out the back. And that's another thing where the Quadro cards and other professional cards tend to default to that. That's kind of the cooling option that those default to. On the consumer side, you have to do a little bit more work to find those video cards that have that type of cooling. So you can just physically look at the cards. I've shown examples there of multi-fan versus single fan. That'll give you a good idea just looking at the cards. But something you want to definitely consider. And also, if you're getting a system with maybe one GPU now, but you want to be able to add more in the future, you don't want to have to swap out that primary video card you've got later on. So going ahead and getting a single fan card from the get-go, even if it's just one, if you're thinking about upgrading to multiple cards, is a good way to go. And it's not just the fan on the video card that matters. You also want to make sure there's good airflow through the system. Again, we're talking hundreds of watts of heat potentially here with multiple GPUs. So you want to make sure there's plenty of fresh air intakes on the system to feed those fans on the video cards. You want to kind of keep a balance between the air coming in and going out. A rough shorthand is one good size intake fan for every 1 to 2 video cards in the system. It's a lot more complex because there are different sizes and different speeds of fans, but that's a ballpark estimate. Again, the main idea is you just want to make sure that you're keeping enough airflow into the system to balance out with the exhaust from the cards and any other exhaust fans in the system as well. And so in summary, we've kind of covered everything, I think, pretty well. GPU-based rendering engines are faster than traditional CPU-based engines. There's some downsides, but those are being worked through. And there's also a lot of improvements coming, especially that RTX technology is going to be huge in terms of making GPU-based rendering even faster. You can also stack a lot of processing power into a single system, but you've got to plan and select hardware properly in order to make sure that you end up with a system that's reliable and going to keep cool. If you end up with a system that's stacked with video cards, but they're not breathing well, there's not enough circulation and airflow, I've seen performance drop by as much as 30 or 40% of the whole system. And that's just going to kill your rendering performance. You're only going to be getting a fraction of what you paid for. And at the end of the day, we're here to help. So if you're looking to get a new workstation and you don't want to have to worry about all the different hardware selection options out there, you can come to us, talk to our sales guys. They'll walk you through what all you're doing with the system, what engines you're using, what other software, and we'll tailor a system to your needs and budget. And if you're not able to buy from us for some reason, we do only sell systems within the United States. There's also a ton of information on our website, so you can use that to help you make educated choices if you're building a system yourself. or have to buy it somewhere else. But we just want to help you. We want to make sure you're freed up to do your creative work and you're not having to worry about the computer. So again, there's a question and answer section on the webinar here. Please feel free to submit questions. It looks like there's 1 or 2 already coming in. I'll address those here in a moment. And I'd be happy to answer any questions you've got. You can also reach out. We have comment sections on all of our articles, so you're welcome to come there and interact and ask questions. And then again, if you are looking for a system, certainly feel free to reach out to us. In fact, this last slide here has information for email and phone contact for our sales department, as well as a nice short URL you can go to if you want to go straight to our recommendations for rendering systems. And again, there's also articles and all sorts of other resources on our website. So let's take a look at the questions here. Looks like we've got one. I'm currently finishing a workstation setup containing 4 NVIDIA Titan RTX. Okay, just a heads up there, the Titans are only available in the multi-fan design. 4 of them is going to be a bit dicey with that. You're going to want really, really good airflow in the system, and even then, can't promise that's going to work well. The most we've had success with is 2 Titans at a time. Just a heads up there, something to be aware of. I'm currently looking at Redshift 3D as my main GPU rendering engine of choice, as it supports multiple packages within a single license. Yep, that's very true. That's awesome. But I have been wondering if Redshift supports network rendering so I can scale across multiple systems. That's a good one. We've not tested that on Redshift specifically yet. I don't think they do, is my understanding. I know Octane does. That's one of Octane's big things, and they've actually increased the number of GPUs you can have working on a single thing, even across networked systems. I would recommend reaching out to Maxon, because that might be changing now that they've switched ownership and sort of been being integrated into Maxon. But I've had some good talks with folks at Maxon, at SIGGRAPH actually. I don't think I asked about that though. So my impression is I don't think it supports network rendering, but I would double check with them directly. And that also may be something they're on the cusp of releasing Redshift 3 supposedly later this year. That's going to be what adds RTX support. It might well be that things like that are changing in there too. Let's see, there's another question here. Why are we only seeing rendering benchmarks on consumer cards rather than Quadro cards? Does Puget recommend using consumer over Quadro for rendering? That depends. Like I said, that biggest advantage for purely GPU rendering with the Quadro cards is the amount of VRAM. You can get more at the same level of performance, and then just more absolutely. The Quadro RTX 8000 with 48 gigabytes of video memory is just an insane amount. That's twice what you get on the Titan and 4 times more than you can get on any of the GeForce cards. So more than 4 times actually. So if you need that extra VRAM, definitely. Outside of that, if you're doing applications that also need a Quadro, like let's say you're doing SolidWorks for product design or some architecture work or something, those applications, a lot of the stuff in the engineering and product design fields recommend or require Quadro cards as well. So if you're doing that, then sure, if you're mixing those uses, go ahead and feel free to go ahead and get a Quadro. The downside is they are just expensive. So folks, especially on a budget who don't need as much VRAM, things like that, you can get a lot more horsepower out of GeForce cards for the price compared to Quadros. So it really can go either way. It depends on your specific situation. That's one of those reasons we put so much emphasis on the consulting side of things when folks come to us, is we can talk through all those things, kind of figure out what's worth it. Is it worth going for fewer GPUs but more VRAM? Is it worth going for more GPUs, less VRAM? How it fits your budget, that sort of thing. But there's definitely, the only downside with Quadro is the price. There's no other reason not to go with them. They're fantastic cards. They just cost a lot of money. Let's see, anything else here? I don't see. I guess we can go ahead and, if it's not already launched, there's a poll here we can fire up for you to kind of get some feedback to make sure that we're, whether we're being too technical, not technical enough, whether there's different types of information you need. We're going to be trying to do a webinar like this about once a month. Last month, my colleague Matt did one on DaVinci Resolve. So we're going to be kind of mixing up topics, but it'd be really helpful to know where we're at in terms of technical level and details. Because in the end, we're doing this for you guys. We want to make sure that we're getting this information out there to people so they can make the best decisions when it comes to getting computers. Yeah, again, I'm very pleased to have been able to do this. I'll give it another minute or so here in case anybody has any questions, but I don't see anything else on here. So I hope you've all enjoyed this. I hope it's been helpful and informative. And again, if you have any other questions, you can also email us. Our contact information, mine is on our website under the About Us section. And you can reach out to us on articles and all sorts of different ways. So we'd be happy to hear from you. And thank you very much.